Pull up a chair. This water runs uphill through 2 centuries of quiet engineering. How a pump with zero electricity moves water uphill. Why Hurricane Isabel proved Amish farms right. The exact lifetime cost that replaces 40 years of water bills. What modern disaster engineers are borrowing from Amish farms. Somewhere in Lancaster County, Pennsylvania, a family of 8 runs a working farm, a dairy operation, and a household, without a water bill. Not this month, not ever. No meter on the wall, no utility company on the phone, no municipal connection at the road. Their great-great-grandparents built a water system in the early 1800s, and the logic of it has never needed replacing. The pipes are different now, the troughs are newer. But the core idea is identical to what was laid down 2 centuries ago. It works so well that nobody bothered to change it. This video is about that idea, where it came from, how it actually functions, and why it quietly solves problems that modern infrastructure is still struggling with today. The Amish are not one group with one set of rules. They are dozens of communities, Old Order, New Order, Beachy, Schwarzentruber, each with its own set of practices called the Ordnung. But across nearly all of these groups, one rule holds steady: no connection to the public utility grid. That means no municipal water, no electric pump pulling from a city main. Whatever water a family needs, they must source, move, and store themselves. This is not a recent protest against modernity. It goes back to the founding logic of Amish settlement in America, which began in earnest in the early 1700s in Pennsylvania. The Amish came from German-speaking Switzerland and Alsace. They were Anabaptists, a reform movement that broke from the Catholic and early Protestant churches in the 1520s. They believed the church should be separate from state power, and they paid for that belief in exile and persecution across Europe. By the time William Penn opened Pennsylvania to religious refugees beginning in 1681, the Anabaptists were ready to go. They settled in fertile limestone valleys, built farms, and began organizing community life around a principle they had carried from Europe: Gelassenheit. It translates roughly as yielding to God's order and to the community. Self-reliance was part of that. Dependence on outside systems was not. When the first Amish farms went in, there was no municipal water anyway. Every European settler in 18th century Pennsylvania did what the Amish still do. You find a spring, you dig a well, you root a stream, you store what you collect. The difference is that when municipal water arrived in the 19th century, most rural Americans eventually connected to it. The Amish, for theological and community reasons, did not. So the old system kept running, kept being maintained, kept being passed from parents to children. And over roughly 200 years of iteration, of problems found and solved, of pipes swapped and cisterns redesigned, it became something surprisingly refined. Not primitive, refined. The foundation of every Amish water system is the same: gravity. Not electricity, not pressure from a utility main. Gravity. Water sits higher than where it needs to go, and it moves downhill. You collect water at a high point, a spring, a rooftop, a hillside cistern, and you let physics do the rest. A spring fed by an uphill aquifer can deliver water to a farmhouse continuously at steady pressure with zero energy input. For communities that avoid grid electricity, this is not a workaround. It is the system. And it produces something that surprises engineers who study it: consistent pressure, consistent flow, no pump failures, no power outages. The water just arrives. There are 4 main water sources that Amish farms use, and most farms use more than one. Springs, drilled wells with hand pumps or pneumatic pumps, rainwater catchment from roofs, and surface water from ponds or streams. Each source gets stored and routed differently. Springs are the most prized because they run continuously and require the least effort to manage. A strong hillside spring can supply an entire farm indefinitely. Wells are reliable but require lifting either by hand or by a system we will look at closely later. Rainwater catchment is used heavily in areas where springs are scarce, and surface water is mostly for livestock. The genius of these systems is how they combine sources to create redundancy. If one fails, another carries the load. To understand how the Amish moved water before any kind of mechanical pump existed on their farms, you need to understand one device: the ram pump. The physics behind it were understood in Europe by the 1700s, and the device was refined into a practical form by the French engineer Joseph Michel Montgolfier in 1796, the same man who co-invented the first hot air balloon with his brother Etienne. The ram pump arrived in Pennsylvania with the wave of European technical knowledge that flooded the colonies after the Revolution, and it matched Amish needs almost perfectly. Here is how a ram pump works. A stream or spring feeds water down a pipe at a slight slope, the drive pipe. As the water accelerates, it hits a check valve and slams it shut. The sudden stop creates a pressure spike. That spike is enough to force a small volume of water through a second valve and up a delivery pipe to a tank that can sit 10, 20, even 30 feet higher than the pump. Then the first valve opens, the cycle resets, and the pump beats again. It sounds like a slow heartbeat: thump, pause, thump, pause. It runs 24 hours a day on nothing but the energy of falling water. One ram pump can lift water to a tank on a hill above the house, and gravity from that tank then pressurizes the entire farm. The elevated storage tank is the second critical element. Once you have a tank sitting higher than your farmhouse, kitchen, and barn, you have running water everywhere below it. The tank might hold 200 to 1,500 gallons. It might be a wooden barrel on a stand, a galvanized steel tank in the late 1800s, or a polyethylene tank today. The Amish replace materials as better ones become available. They are not opposed to better pipes or better containers. What they maintain is the architecture. Gravity fed in, gravity fed out. The tank acts as a buffer. When demand is low, it fills. When you open multiple taps in the dairy barn and the kitchen at once, the stored volume handles the surge. No pressure tank needed, no pump kicks on. Dairy farming makes the water demands on an Amish farm enormous. A single dairy cow drinks 30 to 50 gallons of water per day. A herd of 30 cows needs 1,000 to 1,500 gallons daily just for drinking, before you account for milking equipment, washing, udder cleaning, and barn sanitation. Modern dairy farms handle this with electric pumps and municipal supply or deep-drilled wells with electric submersible pumps. Amish dairy farms handle it the same way they always have. The ram pump fills the hilltop tank overnight. The tank gravity feeds the barn troughs. The troughs have float valves, simple ball and arm mechanisms that shut off flow when the trough is full, exactly like a toilet tank. The cows drink. The float drops. The valve opens. No human attention required. Windmills entered the Amish toolkit in the mid-1800s. The American farm windmill, the kind you see across the Midwest with a multi-bladed wheel on a tall tower, was commercialized in the 1850s, though early models used wooden vanes. Steel wheels became standard only from the 1890s onward, and quickly became standard equipment for farms without strong springs. For the Amish, a windmill is a perfect technology. It requires no fuel. It connects to no grid. It has moving parts that a skilled farmer can maintain with hand tools. The windmill pumps water from a drilled well into the same elevated storage system. On a windy day, it overfills the tank. On a calm day, the stored water carries the farm. In areas where springs are weak or absent, windmills became the primary water source, and they are still running on Amish farms across Ohio, Indiana, and Iowa today. Pneumatic pressure systems are another technology. Many Amish communities permit, and this one surprises people. A pneumatic pump uses compressed air, not electricity, to push water through pipes. The air is compressed by a windmill, a hand pump, or a small gasoline engine in communities that permit them. The compressed air sits in a sealed tank, and that air pressure pushes water into the house lines. This gives kitchen faucets genuine water pressure, comparable to what you feel in a suburban house. Some Amish kitchens are indistinguishable from modern ones in terms of water delivery. The difference is invisible. It's behind the wall, no electric pump, no utility meter, no monthly bill. Spring boxes are one of the oldest and most elegant pieces of the Amish water system. A spring box is a small stone or concrete chamber built directly over a natural spring. It does three things at once. It captures the spring's output cleanly, preventing surface water and animals from contaminating it. It creates a small reservoir, a few hundred gallons, that smooths out variations in spring flow. And it keeps the water cold because it sits underground. A properly built spring box can keep water at 50 to 55 degrees Fahrenheit year-round, which is cold enough to inhibit bacterial growth. Before refrigeration, Amish and non-Amish farmers alike used spring boxes to keep milk and butter cool. The spring house, a small building over the spring box, was standard infrastructure on any serious Pennsylvania farm well into the 20th century. The construction of a gravity-fed Amish water system follows a specific logic, and it starts with a survey that any experienced Amish farmer can do himself. You need to know the elevation difference between your water source and your storage tank, and between your storage tank and your lowest outlet. More elevation difference means more pressure. The rule of thumb is simple. Every 231 feet of vertical drop gives you 1 pound per square inch of water pressure. A tank sitting 46 feet above your kitchen faucet delivers 20 pounds per square inch. That is low by municipal standards. City water runs at 40 to 80 psi, but it is enough to fill a sink, run a shower, and supply a dairy barn without any mechanical assistance at all. Pipe materials have changed over the generations, and the Amish have changed with them. The earliest systems used hollowed logs, bored out with an auger and fitted together, end to end. Lead pipe followed, then cast iron, then galvanized steel, then copper, and now primarily polyethylene and PVC. Each transition happened for the same reason. The new material was cheaper, more durable, or easier to work with hand tools. The Amish are not Luddites rejecting all new materials. They are pragmatists who adopt what improves function while rejecting what creates dependency on outside systems. A PVC pipe installed by hand is fine. An electric pump that requires a utility company to function is not. Water quality is a real concern in any private system, and the Amish approach it seriously. Spring water is generally clean if the spring box is properly built and the watershed above it is not contaminated. Well water can contain iron, sulfur, or bacteria, depending on local geology. Most Amish communities test their water. Some use simple sand and gravel filters built into the spring box. Others use UV sterilization, a technology that runs on 12-volt DC power, which many communities permit because it does not connect to the grid. A few use ceramic pot filters or charcoal filters. The approach varies by community and by local water quality. What is consistent is that the responsibility sits with the family and the community, not a distant utility. The community dimension of Amish water systems deserves attention. When a new family needs a water system, a young couple building their first farm, or a family moving to a new settlement, the community builds it together. A barn raising gets all the attention in popular culture, but a spring box construction, a pipe laying day, a well drilling. These are also communal events. Experienced farmers share knowledge. Younger men learn by doing. There is no plumber to call and no permit to file in most rural jurisdictions for a private spring system. The knowledge lives in the community rather than in a licensed professional class. When a problem arises, a spring runs low in drought, a pipe cracks in winter, neighbors help diagnose and fix it. Droughts test gravity-fed systems hard. A spring that runs strong in April may slow to a trickle by August. Amish farmers in drought-prone areas have developed layered responses. First, they build larger storage, tank-sized not for daily use but for a week or more of reserve. Second, they maintain multiple sources, so if a spring falters, A well or a rainwater cistern takes the load. Third, they reduce consumption during dry periods in ways that are difficult for a utility-connected household to do, because the Amish can see their water level in the tank. When it drops, you use less. There is no abstract bill arriving weeks later. The feedback is direct and visible. That visibility turns out to be a powerful conservation tool. Rainwater harvesting adds another layer of resilience. A standard Amish farmhouse has a large roof, often 2,000 square feet or more of catchment area. In a region that receives 40 inches of rain per year, that roof can theoretically collect over 40,000 gallons annually. In practice, losses to evaporation and overflow reduce that number, but even capturing 20% of it, 8,000 gallons, is a meaningful supplement. Gutters route runoff into underground cisterns, typically built from poured concrete. A first flush diverter, a simple pipe arrangement that discards the first few gallons of rain, which carry the most roof contamination, is standard practice on well-designed systems. The cistern water is used primarily for laundry and livestock rather than drinking. Here is where the story takes a turn that most people don't expect. Modern water engineers, people who design municipal systems, disaster relief infrastructure, and water systems for remote communities in the developing world, have started studying Amish farms deliberately, not as historical curiosities, as engineering models. Because the Amish solved a problem that disaster relief has not. When a hurricane or earthquake knocks out grid power, municipal water fails within hours. Pumps stop, pressure drops, pipes lose their flow. Communities that depend entirely on electric pumps and utility mains are suddenly without water. An Amish gravity-fed spring system with a full hilltop tank keeps running through a blackout indefinitely. It was never connected to anything that could fail. The resilience argument is not theoretical. When Hurricane Isabel hit Pennsylvania in 2003, large portions of Lancaster County lost power for days. Municipal water service was disrupted in several boroughs. Amish farms in the same county kept running without interruption. The spring kept feeding the tank. The tank kept feeding the house. The dairy barn troughs kept filling. The difference was visible and discussed at the county level, not widely publicized but noted by engineers and emergency managers who were paying attention. Amish farmers, when asked about it, had no particular comment. The system worked the way it always worked. That was the point. The financial picture is striking when you lay it out. A typical American household pays somewhere between $400 and others $200 per year for water and sewer service. Over a 30-year farm mortgage, that is $12,000 to $36,000 in utility payments, before rate increases, which have averaged around 5% annually in most U.S. municipalities over the past 20 years. An Amish water system costs money to build. A drilled well might run $8,000 to $15,000, a ram pump $300 to $800, storage tanks another $500 to $2,000, piping a few $100s. But the system then runs for decades with minimal maintenance costs. The capital expense is front-loaded. The ongoing cost is close to zero. Maintenance is where the Amish system requires something that money cannot buy: knowledge and attention. A ram pump has internal valves and a pressure chamber that need periodic inspection. Every few years, the rubber flap valves wear and need replacement. The parts cost a few dollars. The repair takes an hour for someone who knows the mechanism. A spring box needs to be cleaned of sediment every year or two. Pipes in northern climates need to be either buried below frost depth or drained before winter. An elevated tank needs its float valve checked seasonally. None of this is complicated, but it requires the farmer to understand his system well enough to catch problems early. A cracked fitting, a slowing spring, a tank that won't fill to capacity. That knowledge is the real infrastructure. There is a specific knowledge transfer moment in Amish communities that is worth describing. When a son or daughter prepares to set up their own farm, typically in their early 20s, the father walks the entire water system with them, not once, multiple times across multiple seasons. He shows where the spring runs from, how to read the flow rate, where the pipes are buried, how deep, what material, and what to do when the ram pump goes quiet. This walkthrough is not written down. It does not need to be. The system is simple enough that a thorough oral and hands-on education covers it completely. The knowledge has been passed this way for 7 or 8 generations in the oldest Amish communities. Newer Amish settlements in Kentucky, Missouri, Montana, and upstate New York face water challenges different from Lancaster County's limestone aquifers. Some sites have no strong springs. Some have hard water loaded with iron. Some sit on land where the water table is 200 feet down, too deep for a hand pump. These settlers have adapted. Deep drilled wells with windmill pumps, larger rainwater cisterns, sand and activated charcoal filters for iron and sulfur. In a few cases, communities have negotiated shared spring systems across multiple neighboring farms, running a common pipe from a single strong spring and splitting flow at a junction box. Each household maintains its own section. The communal logic extends to the infrastructure. The question of what happens when a spring site simply does not exist comes up in any discussion of off-grid water. In flat land with a high water table, much of Indiana, for example, there is no hill to put a tank on, no natural spring pressure, no ram pump opportunity. Amish farms in these areas rely primarily on windmill-powered well pumps filling elevated tanks on towers. A tower 20 to 30 feet tall gives enough head pressure for basic household use. Some farms use air-over-water systems where a windmill compresses air into a sealed tank, and that air pressure pushes water from the well into the house. The architecture shifts to fit the landscape. The principle, no grid dependency, stays fixed. By the early morning of a typical Amish farming day, the water system has already been working for hours with no human involvement. The spring ran overnight. The tank filled. The float valves in the barn closed when the troughs reached capacity. The dairy wash lines have water waiting. A farm family of 6 to 8 people, running 30 dairy cows, a large vegetable garden, and a household, may use 300 to 500 gallons of water on a heavy day. The elevated tank holds 500 gallons. The spring replenishes it continuously. The farm's water cycle is complete before the first lamp is lit. This is what 200 years of iteration looks like when the solution fits the landscape perfectly. The sustainability angle is not lost on researchers. Conventional municipal water requires enormous energy inputs. Water must be pumped from source to treatment plant, treated with chemicals, pumped again to elevated storage, distributed through pressurized mains, and then the used water must be collected and pumped to a sewage treatment facility. Environmental Protection Agency estimates that water and wastewater services account for roughly 2% of national energy use. A figure that sounds small until you realize it represents tens of billions of kilowatt-hours per year. An Amish gravity-fed system uses no grid energy for water delivery at any stage. The energy input is geological, water falling as rain, soaking into the ground, and emerging uphill under natural pressure. One criticism of private spring and well systems is contamination risk. Without a utility company monitoring water quality, how do Amish families know their water is safe? The honest answer is that some do not test as rigorously as they should, and waterborne illness in rural communities, Amish and non-Amish alike, is more common than in municipal systems. The Centers for Disease Control and Prevention has documented outbreaks linked to private well water in rural Pennsylvania, and Amish communities have not been immune. But the more thoughtful Amish approach, annual testing, proper springbox construction, separation of animal waste from water sources, produces water quality that meets or exceeds EPA standards for private wells, according to assessments done by Penn State Extension researchers who have worked directly with Lancaster County communities. The off-grid water movement, homesteaders, permaculture farms, rural self-sufficiency communities, has essentially rediscovered everything the Amish never stopped doing. Gravity-fed spring systems, ram pumps, spring boxes, elevated tanks, float valves, rainwater cisterns. All of these appear in contemporary off-grid water design guides as innovations. They are not innovations. They are standard Amish infrastructure refined over 2 centuries. Brad Lancaster, whose books on rainwater harvesting have become standard references in the off-grid community, documents systems structurally identical to what Amish farms have used since the 1820s. The knowledge was never lost. It was just not visible to the mainstream because the people using it were deliberately living outside of it. Climate change adds a new urgency to this conversation. In regions where aquifers are dropping, the Central Valley of California, the Ogallala Aquifer beneath the Great Plains, gravity-fed spring systems are not the answer because there are no springs to feed them. But the principles behind Amish water resilience, redundant sources, local storage, direct feedback, low energy dependency, are exactly what water engineers are now trying to build into municipal systems that have grown too centralized and too fragile. The 2021 Texas freeze that left millions without water for days was, at its core, a failure of a system with no resilience architecture. Every Amish farm in Lancaster County has resilience architecture. It is just built from stone and pipe and elevation rather than policy and infrastructure budgets. There is a question that always comes up when people learn about Amish water systems. Would this work for everyone? The honest answer is mostly no, and the Amish would not want it to. The system works because of specific geographic conditions: limestone aquifers, rolling terrain, adequate rainfall, that exist in Lancaster County and in many but not all Amish settlement areas. It works because of knowledge that takes a lifetime to acquire and a community to transmit. It works because the community maintains a culture of attention to the land, to the water, to the infrastructure. You cannot extract the ram pump from that cultural context and sell it as a product. The pump is not the system. The community that knows how to maintain it is the system. What the Amish water system represents in engineering terms is something called passive reliability. The system has no active components that require external energy or real-time monitoring to function. It cannot fail because the grid failed. It cannot fail because a pump motor burned out. It can only fail if the water source itself runs dry or if a pipe breaks. And both of those failures are visible, local, and fixable with hand tools in an afternoon. Passive reliability is considered extremely difficult to achieve in large-scale infrastructure precisely because scale requires active management. But at farm scale, the scale at which human beings actually live, passive reliability is achievable. The Amish have been demonstrating this for 200 years, and they did not need to publish a paper about it. The broader lesson is about the relationship between simplicity and resilience. Modern water infrastructure is extraordinarily capable. It treats millions of gallons to drinking water standards, monitors for dozens of contaminants, and delivers water under pressure to urban populations that could not survive without it. No one is arguing that Lancaster County's spring boxes should replace Chicago's water system. But there is a spectrum between a hilltop spring box and a billion-dollar treatment plant, and somewhere on that spectrum a great deal of value has been abandoned. Distributed systems, local knowledge, redundant sources, low energy dependency. They became radical only when the dominant infrastructure moved so far away from them that the alternative looked like poverty rather than prudence. Young Amish farmers today learn to use laser levels and soil permeability tests alongside the older techniques. Some use drilled well logs and hydrogeological surveys to site their wells more precisely. The tools improve. The architecture does not change. In the most progressive Amish communities, solar-powered DC pumps have been approved for use in some situations because a 12-volt solar pump running off a rooftop panel does not connect to the grid and does not create dependency on a utility company. It is a living document, debated and revised by community councils. The consistent outcome across those debates for 200 years is that the water system keeps its core principle intact. The specific numbers are worth sitting with for a moment. An Amish farm family over a 40-year farming career will spend roughly $3,000 to $10,000 on their total water infrastructure. Well drilling, pump installation, tanks, pipes, and maintenance combined. A comparable non-Amish farm connected to municipal water will spend $20,000 to $50,000 on water and sewer bills alone over the same period, not counting private infrastructure. The difference is not just financial. The Amish farmer understands every component of the system. He can fix anything that breaks. He is not dependent on a call to a service department or a billing cycle or a rate decision made by a municipal board 30 miles away. That independence has a value that does not show up in any financial comparison. 200 years is a long time for any technology to keep working without fundamental revision. The Roman aqueducts worked for 500 years before their maintenance systems collapsed. The Amish water system is not an aqueduct. It is simpler than that, which is precisely why it has lasted. It has no single point of failure. It requires no specialized labor class to maintain it. It asks only that each generation learn it from the last, understand why each piece exists, and keep the landscape conditions that make it possible. Those conditions: a spring in the hills, a farm on sloping ground, a family that pays attention, are not guaranteed. But where they exist, the system runs. It ran this morning on farms whose current owners' great-great-grandparents laid the first pipe. That is a record worth thinking about. So when a family in Lancaster County opens the tap this morning and water runs, cold, clear, pressurized, without a utility company, without a monthly bill, and without a pump that needs electricity, they are not doing something exotic. They are doing something old. And in doing something old, they have ended up doing something that most modern infrastructure cannot match: a water system that works through power outages, droughts, and economic disruptions without missing a beat. The question is what we gave up when we decided that water was someone else's problem to solve. Give me your take in the comments below.